term today is Artemis Megan from Euclidean, who tells about homogeneous Riemann surfaces.
Thank you, Vivica, and thank you for the introduction, and thank you to Ernesto and Gabino for putting this together. It's already been a wonderful stay, and possibly after this talk, momentous. So, what I want to tell you about is quasi-formal homogeneity of Riemann surfaces. So, what am I talking about here? Well, as Gabino pointed out, homogeneous can mean lots of different things. So, you can ask, in what sense do you mean? Of course, that's the correct question. And the first thing you can ask is, first of all, with homogeneous, what I mean is you have some group, ambient group, and you're asking, which is a group of homeomorphisms on the surface, and you're asking for transitivity on the surface. So in other words, given any 2 points, there's a map, an element of the group that maps one to the other. Actually, I said group, but it's a family of maps. It's not a group, not necessarily. So the easiest thing is to say diffeomorphisms. Of course, any 2 points can be moved under a diffeomorphism of the surface. That's pretty easy to see. So then you need a little finer notion than diffeomorphic to sort of make sense of things. Well, you can go to conformal. Okay, so if you go to conformal, there aren't that many Riemann. So now you have a Riemann surface structure on your surface, and you're asking for, is there a conformal map between any 2 points of the surface? Well, there's a very particular list of surfaces that satisfy that, including the hyperbolic plane and the complex plane and a few others I'll write down. But that's about it in terms of conformal homogeneity. So then the right notion seems to be somewhere between diffeomorphism, where you're allowing unbounded eccentricity, versus no eccentricity. In other words, infinitesimal circles get mapped to infinitesimal circles. So the right notion then is the notion of quasi-conformal. And so that's what this talk is about, really, quasi-conformally homogeneous Riemann surfaces. And what I mean by that, I'll explain. What I really mean is you have a K, and between any 2 points, there's a K quasi-conformal mapping of the Riemann surface to itself that maps those one point to the other. So that's what I'm about to say. And any of the new stuff I'm talking about is joint verb with new planets. And any of the old stuff I'm talking about is old. I mentioned this. Okay, so do this. So I'll start with a hyperbolic manifold, but I'm going to quickly go to surfaces after you see the theorem that's already been proven by a long list. There's a long list of people that have worked on this question of homogeneity, QC homogeneity of surfaces or manifolds, hyperbolic manifolds. So let's start with a hyperbolic manifold. So you have a hyperbolic manifold X, and we'll say that it's KQC homogeneous. Whoops. Uh-oh. So, yeah. So we'll say that it's KQC homogeneous, or KQCH, if for any 2 points there's a KQC map F mapping the hyperbolic manifold to itself that takes that 1 point to the other. Okay? So, by the way, what does quasi-conformal mean in this category? What you should be thinking is infinitesimal spheres get mapped to ellipsoids in higher dimensions, ellipsoids with bounded eccentricity, uniformly bounded eccentricity. Okay? There's a little bit of discussion because these are really homeomorphisms, not diffeomorphisms, but you might as well just be thinking of diffeomorphisms. And if you don't like quasi-conformal maps, for most of what I'm going to say, it's good enough to be just thinking about bi-Lipschitz maps. Same thing holds. So I'll say that the manifold, the hyperbolic manifold, is QCH if there is some K that makes it KQCH. Okay? So Gehring and Polka introduced this notion of QCH, and then there's a list of authors, but Bonford Taylor, Canary, and Taylor, along with various co-authors, wrote a series of papers investigating these objects, and I could spend an hour just talking about the history of all the things they've gone through, including there's Juan Soto in this list, Gavin Martin. But these were the main authors of the original articles, and the main theorem that that I'm gonna cite from them sort of nails where I'm going, and then we're gonna go down to the next two quickly. So let me start with an example of a hyperbolic manifold that's QCH. Okay, so I didn't write it down, but the obvious one is HN is QCH for K equals 1. Okay, but let's get a little more exotic. If you take any closed hyperbolic manifold, that's QCH, just from a compactness argument. But if you don't like that, you can say, given any 2 points, you take a path between those points, a minimizing path between those points, and then cover it with balls of radius epsilon or something. And then in each one of those, you could find for high enough K, you could find a KQC map that sort of moves you along, and then you compose these two, and then this series of maps. And then you get a map that maps that point X to the point Y with uniformly bounded eccentricity. So you can do that. So any closed hyperbolic manifold is KQC. But more exotic is if you start with surface cross I, and then you have a pseudo-Anosov mapping, and you identify the top, bottom to the top, you get the mapping torus. We know that that's hyperbolic. There's Thurston's work, and since it's a closed hyperbolic manifold, that's QCH, but also its Z cover is QCH. Okay? And so that's what this next example is stating. Any geometric regular cover of a closed hyperbolic manifold is KQCH. And you can see how to do this. I'll do this in this example. This is the Z cover of that closed hyperbolic manifold, the mapping torus. Suppose I want to go from this point here. Suppose I had a point there, and I had a point way over there above Ernesto's head. Right? So what you do is, you know there's an isometry, so a 1 QC map that takes this and shifts along down to that, into that region where that other point is. And then this piece is compact, so you can always, with a bounded K, map a point in here to another point in here. So that's the idea, and that's how you could show that any geometric, and I'm emphasizing geometric here, geometric regular cover of a closed hyperbolic surface manifold is also QCH. And in fact, their theorem in dimension bigger than or equal to 3 is that, so this is Bonford Taylor, Canary, Martin, and Taylor, that if you're QCH in dimension bigger than or equal to 3, then you are the geometric regular cover of a essentially closed hyperbolic manifold. Okay? So that's it. And that's because of rigidity. There's rigidity in dimension 3 and higher, non-stop rigidity. So there isn't much else you can do. So our point of view for this talk is going to be, well, let's go to dimension 2 and ask the same questions. Is every closed hyperbolic surface, which is QCH, is it a geometric regular cover? Okay.
That's not what you.
Huh? You're gonna point at something?
No, I don't think you said what was in your head.
Is now you know what's in my head. No. What did I say? I said is every hyperbolic surface that's QCH.
Yeah, you said close. This is one.
Oh, I'm sorry.
Yeah.
Well, that's not what.
That's not what
That's not
was
what
saying. So is every QCH hyperbolic surface?
I'm gonna. Yeah. That's what the rest of the talk. Yeah. Yeah. You don't have like a. What? No, it's okay. I got a scrolling for you. No, it's good. So what happens in dimension 2? Are you okay with that? What happens in dimension 2? That's the question. And I'll give you an example of something. Let's just go right to this example. Okay. So remember that. I'll take 30 seconds so you can look at the picture. I'm very proud of the picture. That's why I want to take 30 seconds. That's why I was up until 1:30 in the morning. All right, so what's happening here is remember that the geometric regular cover, that's always a theorem. The geometric regular cover of a closed hyperbolic manifold, in particular in dimension 2, the geometric regular cover is QCH. Okay, so in this picture, I have a hyperbolic surface here, genus 2. This is its geometric regular cover. It's a Z2 cover of this, and it's QCH by what I just said. But the point is, anything QC equivalent to this, or by Lipschitz equivalent to this, is also QCH, okay? And it's no longer a regular cover, a geometric regular cover. It is still a topological regular cover, but it's no longer a geometric regular cover. So clearly, this theorem is false in dimension 2, okay? That all QCHs are geometric regular covers. But something's going on here, so that's what the content of this talk is about, and our work is to investigate that in terms of this question of covers. Okay? So an important thing I want to emphasize.
Yeah, so it's just bound. Okay, so it's macro dilatation is bounded.
Maximal dilatation is bounded. Yeah, by QCH I mean uniformly bounded.
Yeah, but if you move the point to the other cover, then so repeating this thing, then dilatation may be bigger. Because the composition is
No, but so in this example, what I did was, can you tell back there? This geodesic is very, very small. I made this one smaller, kept everything else the same.
But you did copy paste it, right? And then
I think you can change the color.
I learned how to use this from you, so. If you don't like this, ignore the picture. If this is a QC map between these two Riemann surfaces, then definitely this is QCH. Definitely.
So only QC constant differs by this map.
Yeah. So it's the upper bound is going to be the product. Right. Okay. Is that okay? I have next to no agenda, by the way. So you could stop me as often as you like, and I have a feeling I'm going to be stopped a lot. That's fine. So the focus is on dimension 2, surfaces. So if we forget about hyperbolic for the moment and just talk about Riemann surfaces being one complex dimensional, just some background quickly. If the fundamental group is not abelian of the Riemann surface, then it has this property that there's a unique hyperbolic metric associated to the conformal structure of the surface. But now let me address the question of which ones are conformally homogeneous. That's it. That's it. None of them are hyperbolic, by the way. Right, so the unit disk, the complex plane, the Riemann sphere, the punctured plane, and the torus are all conformally homogeneous. K is
Your
1.
disk is hyperbolic.
My disk is, oh, whoops, yeah. Yeah. Well, you know, I wasn't good about drawing, so maybe this is not so much a disk. Yeah. So all of these are 1 plus conformal. So before I get to, so our goal is to understand covers of QCH surfaces, okay? And to classify them both, ask the question for topological covers and then geometric covers. Okay? So before I do that, a couple of properties for your entertainment pleasure. So QC maps in the large, so I'm going to talk about them in the large for the moment, and then I'm going to talk about them in the small. So in the large, they're basically bi-Lipschitz map, coarse bi-Lipschitz maps. So if you have a KQC map, it's a quasi-isometry with these constants. So that is, it looks like this. So in the large, it's basically looks like a bi-Lipschitz map. Okay, we're up to the additive constant. It's a bi-Lipschitz map. So because of that, we have two consequences. You can't have embedded half-planes, and in particular, no funnels if you're QCH. Here's the picture. You see, here's a surface with a hyperbolic surface with a funnel, right? So you have this large embedded half-plane, as big as you like out here, and if I take a very large disk over here, and I want to map it by a KQC map of this surface to this point here, well, since this is a bi-Lipschitz map, essentially, this image of this disk has to contain a disk of radius 1 over kr, if k was the rotation, okay? And if I take r to be larger and larger, there's no way this is going to be satisfied. The injectivity radius at this point is bounded. Okay? So there's no way you could have, there are no embedded half-planes, in particular funnels. I'm saying it this way in terms of half-planes because when you go to infinite type surfaces have this extra feature where to complete them, you don't just add necessarily funnels, you might have to add half-planes. More about that later. Is that okay? Yep. Okay. So that was in the large. What about in the small? Okay. So in the small, if you have a KQC map, the distance from f of x to f of y, so if f is a KQC from between two Riemann surfaces, the distance is bounded from below by some function of the distance from x to y. This function can be written down, and complex analysts know this very well. This is a R10 of a tan of something, R10 of a constant times a tan of something. But anyway, you can write this down, this function, and the important feature of this function is it's essentially bigger than x to the k. Okay? K is the dilatation. Okay? So as x gets close to 0. So when x is close to 0, oh, I'm sorry, this x is not this x. My bad. This should be an r. Sorry. So what happens is that when you're in the small, and here's a picture. The implication of this other line is that the injectivity radius, the implication of this, whoops, yeah, I can't get it all on here. The implication is that the injectivity radius at the image of a point is always bigger than this function of the injectivity radius of x. Okay? So that implies there are no cusps on the QCH surface because, well, there it is, right? If I took x to be, I don't know, which way does it go? Yeah, if I took x to be over here somewhere and I want to map it way out here by a KQC map, can't do it. Injectivity radius goes to 0 if you move this way. Okay? There's actually a stronger thing you could say in terms of using the Margulis constant, but this is good enough for our purposes. So the upshot is, so summary, whoops, let's go here. So summary, QCH surface has no cusps or half planes, and what that really means, well, not having half planes means that you can't have funnels or anything. So if you actually look at the convex core, I'm not going to define it, but it's the geodesic subsurface. It's the geodesic subsurface that contains all the topology, all the homotopy. The convex core of the Riemann surface is exactly equal to the Riemann surface. It's complete. Okay, so if you're QCH, you have to be a complete surface. Okay. And so one consequence is, if the surface is topologically finite, then the QCH hyperbolic surfaces are exactly the closed surfaces. Okay. There are no others. You can't have funnels. Okay, so now we should move to infinite type. Things get exotic.
Is it, sorry, this question. In the K, the optimal, say K classical formality constant, is it related to the extremal system of the...
Yeah, that's a good question. It's related. It's related.
So that
It's
does it
related,
go,
because you can
does it go the same way to the bound of the modular space, or?
You mean as the system goes to 0?
Yeah.
What do you mean? Yeah, sure, right, because the injectivity radius has to go up. So there's a lot written about this. But yeah, so this is a good question. What is the optimal K? Questions along those lines. I've ignored all that. I've just been busy with K. You're absolutely right.
All right, is there a single surface for which we know? Is there
no.
any
Yeah, there is.
surface for which
There is.
K is different from one?
Yeah.
K different from one?
Right.
Is there a
No,
single
no,
example?
no, we don't. We have balance.
Yeah, but I don't,
Yeah.
That's
No, we
what
don't.
that we don't have a
Yeah.
single example.
Yeah. No, it's very hard to come up with, nailing down the K. But that's not what you're asking. Okay? You're asking just for the...
Yeah, that's the topics.
Okay, is this okay? Okay, so we're going to shift to infinite type. So here's the question. Can we classify QCH surfaces in terms of regular covers where, let's ask the question topologically first, and then let's ask the more particular question geometrically. So, is every QCH surface a topologically regular cover? And then we'll ask the question, is it a geometric regular cover? So here's theorem 1. If I could get this in here. Is there a way to get rid of this? No, probably not. Okay.
You can get rid of the authors.
Okay, so keep this in mind. Okay, so read this first. You see this line? So we're starting with a QCH surface. Riemann surface. Okay, and get rid of the order. Okay, and pi was not abelian, so it's a hyperbolic surface. Okay? So the statement is that then the surface has to be homeomorphic to one of these, actually 5. So let me explain this. So remember, I'm starting with a QCH surface. So the surface is either homeomorphic to a closed surface. It's the first thing that can happen. That's obvious because of what we said before. It could be homeomorphic to the Loch Ness monster. That's the Loch Ness monster, one end, infinite genus. Okay. It could be homeomorphic to the ladder surface, 2 ends, infinite genus on both sides. Or it could be a Cantor tree surface, which means if you take away the red for the moment, these are just, you can think of these as pairs of pants glued on one and the other, and the end space is a Cantor set. Or the other thing it could be is a blooming Cantor tree, which is just attach a handle in each one of the pairs of pants. And that's it. That's it for the topology of these. So to appreciate this statement, you should realize that there are uncountably many infinite topologically infinite type surfaces. Uncountably many. And we're just picking off, there's only 5 that live in this world. So a corollary of this, each one of these are covers, topological covers. So,
Ara,
yep.
that example you had before with the sort of like the grid surface, which one of those is that? Is that a blooming Cantor tree in some sort of...
That's the Loch Ness monster. That's the same as the Loch Ness monster, because that guy that goes off like this has infinite genus with one end. That's right. That's an exercise in Spherical, volume 1. If you look, if I remember correctly from grad school, there's an exercise to prove that infinite jungle tree, I think it's called infinite jungle gym, is homeomorphic to that Loch Ness monster. I think that's in Spherical. Could be wrong. Volume 1, believe it or not, volume 1, because there's a lot of differential topology in volume 1. I think it's an exercise. It's been a long time since graduate school, and everybody's going this way, so. But I think that's right. So a consequence of this is what I just said. A QCH Riemann surface where it's hyperbolic, pi 1 is not abelian, is topologically a regular cover of a closed surface. Okay. So the proof of this, let me just. So this is what I was just saying before. There's uncountably many topological types of surfaces, but only a small number of these 5 can be QCH surfaces. So the proof is really easy for this theorem 1. So if you start with a QCH hyperbolic surface, assume that it's not a closed surface, because if it's a closed surface, it's definitely a cover of something. So assume it's not a closed surface, so therefore it has to be infinite topological type. Okay, and then first note that you can't have finite genus. You're either genus 0, so except for 0. You're either genus 0 or genus infinity. And the reason is because if you had some finite amount of genus, then what you could do under the being QCH is move that finite piece, a compact part that has genus, as close to any one of the ends as you have. And that's because, remember, F was a QI map, so think of it as a bi-Lipschitz map. So the diameter of this image is bounded from above. I'm missing a parenthesis here. The diameter is bounded from above by the QC constant times the diameter. What did I write? This should be y. This should be y up here. Sorry. Sorry. So if this were right. So what this says is that since the diameter is bounded uniformly by this, if I map this out here, it can't be coming back into a compact part of the region. In other words, I can keep marching out toward that end, which means that that end had to have genus accumulating on it, which means it's I have infinite genus. Okay, so that's so if you have finite genus, it's actually infinite genus. You can't have finite genus except for 0, and all the ends are non-planar because of what this is the same argument. You can march out to any end with genus. Okay, so that's the first part of the argument, and that's the idea of the proof, really. So there's really two cases to consider. One is only planar ends, and the other is so this is genus 0, and then there's the infinite genus case. So let me just talk through the planar end or genus 0 case. No end can be isolated. Why? Well, if you have an isolated end on a hyperbolic surface, it has to come from either a funnel or a cusp. But that violates being QCH. So all the ends are not isolated. But wait, the ends form a closed subspace of the Cantor set, right? And if all ends are limit points, that tells you that this has to be a Cantor set to begin with. Okay, so if the genus is 0, and you're infinitely tight, and you're QCH, then you really have to be topologically a Cantor tree. Your space of ends has to be a Cantor set. And then the argument for infinite genus is simple. Similar kind of argument. So just to recap, the corollary was that so every QCH Riemann surface is a regular topological regular cover of a closed surface. And now let's shift gears and talk about geometric regular covers. And that's the last thing I want to tell you about. So there's a theorem of Barford, Taylor, Canary, Soto, and Taylor. And that's not a good speller. Okay, if he was here, he would be very nice and not say anything. But I would blame him too for not saying anything. So there are exotic QCH surfaces. So what does this mean? So we saw that when you have a geometric regular cover, you could always QC deform it to another topological regular cover that's QCH. But the question is, are all of them geometric regular covers like in the dimension 3 or higher situation? And they constructed an example of a QCH surface that's not the regular cover of a closed hyperbolic surface, not the geometric regular cover. We know it's topological regular cover, but it's not geometric. Okay? And the construction is really interesting, actually. And I'm trying to understand it. What it is the reason why it's not so easy to understand is because it's their construction comes from a construction where they start with, the graphs are called Diester-Leader graphs. And they look at these Diester-Leader graphs, there's parameters involved, and they look at the product of these two of these Diester-Leader graphs, and then they take And the product is a graph also, in a natural sense, and there's sort of a diagonal in there. And you pick off that diagonal, and they show that that diagonal has the property that its automorphism group, as a graph, is transitive, but the graph cannot be the Cayley graph of a finite degenerate group. Okay. So, if you're going to be a geometric regular cover, the one thing you better be is, if you're a geometric regular cover, the Cayley graph of the group action on the cover has to be quasi-symmetric to the Cayley graph of X in the cover. Okay. So by showing, so what do they do? So they construct, so they have this graph, and then they thicken the graph to a surface, and since the automorphism group was transitive, they use that to show that the surface is QCH. You can move from one place to another, roughly with a bi-Lipschitz map, K-bi-Lipschitz map. But there is no Cayley graph because that graph would have been negative. So that graph is not the graph of a Cayley graph. So that's my weak, very weak understanding, and you go through this paper of Fisher, White, and but I think it's very interesting. So there are exotic QCH surfaces. So we know that topologically it's got to be one of these surfaces by the previous discussion of QCH. It's got to be topologically either the Loch-Ness or the lattice surface or the Cantor tree or the Blooming-Cantor tree. And I think it's the Loch-Ness, but I'm not even sure of that because their construction is quite unsure. But I'm here to tell you that we can rule out the ladder surface, and that's the content of this last theorem. If you have a ladder surface, so topologically ladder surface with a hyperbolic metric that's QCH, then it is the QC deformation of a geometric regular cover. So it's not, it cannot be exotic. The QCH structure cannot be exotic. Does that statement make sense? So the argument here is hands-on, and it's building basically, you have this ladder surface, and what you want to do is build sort of a quasi-translation on the surface. Everything is up to quasi. So the first thing you do is sort of try to get break up the surface. So there's a picture. I'm just going to give you step one. So you find, you take some curve, gamma naught, simple curve. So this is the hyperbolic ladder surface, and we're assuming it's QCH. Okay? And I want to build sort of a quasi-translation here, a z-action here. So you take some simple curve here, look at the geodesic in that class, and now go far enough away, and then map it by one of the, you know there's a QC map that takes, say, this point to a point over here, okay? And then the image of this geodesic, you straighten it out to a geodesic, and because these are KQC and the properties of QC maps, there's a certain bound to this distance, okay? Both above and below, and that's what I've written here. The distance, this is the hyperbolic distance between these two. So up here, we're constructing this. Gamma naught goes to gamma 1 by some KQC map. Gamma naught goes to gamma 2 by some KQC map, same K. Gamma naught goes to gamma 3 and so on, and the other way, so on. And then you straighten those curves out, and then those geodesics have this property that the distance is roughly like, this is the parabolic metric, the distance between these geodesic, which is roughly like the difference in the indices, roughly. Okay? So that's sort of a start, because that's allowing us to sort of see if there's some shift now. And then, yeah, and this is the other fact about these curves. They're all bounded by whatever the original length was of gamma naught. These lengths are all bounded from above and below. Because this is a K, K is fixed. KQCH. So the gamma ends are quasi-equally spaced. And then the next step is to realize that between that spacing, and then I'll just give you the light idea of it, in that spacing, I've drawn it in a nice way, but in theory, there could be a lot of genus here. And the genus could, you know it's finite, but you don't know that it's not growing. Okay? So the next discussion is to bound the genus of these from above. And again, you use the bi-Lipschitz property in the large. And then once you do that, then once you know it's got bounded genus, uniformly bounded genus, these chunks have uniformly bounded genus, then, you're done. You use Bayer's Pants decomposition theorem to say that there is a Pants decomposition. These lengths are roughly the same also, right? So now Bayer's Pants decomposition theorem says there is a Pants decomposition of this with bound from above for the lengths. And then you can perpetuate this throughout here. There's a bound from below on the lengths also, because injectivity radius has to be bound from below. This is a QCH surface. And then you have to refine that Pants decomposition to get to the last step. I'm just skipping over a little bit of stuff. Where is it? To get to a Pants decomposition like this, where the Pants curves are bounded, and then you could start to see, now you can move, these geodesics are all independent of each other. They're all within a bound above and below, so you can make them all one in length by a quasi-conformal map. And now you make them all one, and now you have a translation. And then once you have a translation, you've just built the geometric regular cover. Okay? So that's essentially the proof of that. And let me finish with my notes. Great, this is a beautiful piece of paper. This notebook is very good. There's a number of things that arise along the way here. One of which is, you might think that if the surface is QCH, that it has to have a bounded Pants decomposition. And as it turns out, that's not true. So there's a paper that Hugo, myself, and Nick wrote, which is that for any topological type, infinite topological type, there's a hyperbolic structure in which the injectivity radius is bounded from above and below, but there is no Pants decomposition that's bounded. Okay? There is no Pants decomposition. In particular, for the Loch Ness Monster, we have a hyperbolic structure that's QCH, but it does not have a bounded Pants decomposition. That seems almost counterintuitive, but it's not. And this arose. I was talking to Ed Taylor over 20 years ago, and I remember him asking these questions. And these questions swim around all your life, and you pray and hope that before you're going down, something is resolved. So this felt good that we resolved this question. So that's one thing to say. And then the other thing to say is, I've been cavalier in saying that replace QC with QCH with QC maps with bi-Lipschitz maps, and that's definitely, I have a reason for that. But you can also ask the more particular question, which is, everything we've done is about quasi-conformally homogeneous, but you could ask the same question for bi-Lipschitz homogeneous. Okay? And there's a little bit of subtlety, but not that much. You have to use the fact that. So it turns out the category should be the same. I haven't written everything down, but so it should be sort of obvious, and here's the argument. So I'm saying BLH is the same as QSH, QCH. Why? Because, well, any bi-Lipschitz map is a QC map. So the BLH is contained in QCH. All the BLH surfaces are QCH. What about the other way? Well, the point is, if you have a K quasi-conformal map, it's up to it's uniformly close to, uniformly bounded away from a bi-Lipschitz K prime map, where K prime is just a function of K. You can think of that as some people in the audience like this, if you want your own extension, you start with a QC map, mapping of the disk to the cell, you go to the boundary, you come back as a K prime bi-Lipschitz map that respects the fluid. So that's one piece, and then the other piece is, if you're uniformly close with a bi-Lipschitz map, then there's a small enough K bi-Lipschitz map that takes that one point to whatever other remote point. So that's sort of a rough argument that BLH should be the same as QCH. And yeah. Right. I think I'll stop there. Thank you.
So, do you get a new example of a quasi-conformally homogeneous surface that's not a QC deformation?
Yeah.
So, from this example.
Yeah. So we have not. We're not sure. We're not sure because there's a question of whether it's the right thing. Yeah. But so the answer is no right now. But we do get, by that construction, a different hyperbolic structure. I mean, different in the QC sense, so it's really not a QC deformation yeah, so we get a different hyperbolic structure where you have these, so now you have the same Loch Ness monster, you have a QCH structure here, you have a QCH structure here, and there's no QC map between. What we don't know is that maybe this one came from a lower genus and this one came from a higher genus. That's the problem. Maybe that can't happen. So now we do something. That would be satisfying.
Any other questions?
Y no podía soportarlo.
Success. Entonces me parece ya un poco demasiado. Entonces, lo siento por mandarlo. Que ya me habías mandado el...
Sí, ¿no?
Pero
este tiene firma. Y Gaby no me dijo...
Ah, pero nada. Y ahora sí que vais a mandar de que hemos dado charla.
Si lo quieres, sí.
Pero después.
Vale.
Okay, so how does this work?
Yeah.
Is that just the left and right?
Yes, and this is
the top one?
No, the middle
The
one.
middle one there, is that the pointer? Okay, good.
Nobody finds it.
Okay, very good. Okay. Well, first of all, I'd like to thank Gabino and Ernesto for inviting me. As somebody said the other day, this is his first trip. This is actually my first trip to Spain. For some strange reason, I've never ever made it here before, so I'm really pleased to be here. Okay, so there's a table of contents, because we all like tables of contents so that we know when to wake up and when to go to sleep. So basically there's three main chapters, which are going to be a little bit of a historical thing about what Fenchel and Nielsen did back in the 40s. Then I'm going to reinterpret that in language of matrices, and then we're going to generalize. So then here's some history. This goes back slightly beyond the history we heard yesterday from Peter, but obviously not as far as the 18th century maps and everything we had. So terminology. Sigma G is going to be closed, compact, orientable, surface of G is G without boundary, usual thing. G is of course going to be bigger than or equal to 2 because we all like hyperbolic things. Pi 1 is going to just denote its fundamental group. And I'm thinking about this, of course, being base point 3 and all of that. And we want to think about, for some of the talk, representations of that fundamental group into a Lie group. And the Lie group is usually going to be often going to be one of our favourite groups of isometries of some sort of geometrical space, or have some other geometrical connotations. So technically speaking, this is Hom pi 1 of G into G, and then we get rid of conjugation. We have to put these double arrows, double slashes, because this is a GIT quotient, which, if anybody asks me about it, I don't really know very much about it, but I just know that that's a subtle point to do with conjugacy classes. Otherwise you get something that's non-Hausdorff. So back in the 40s, Fenchel and Nielsen, they were thinking about hyperbolic metrics on my fixed surface equal to G, and the space of all metrics with a marking, which of course is Teichmüller space, and they gave global geometrical coordinates, which we're going to construct in a moment. Now, if we want to think about this is equivalent to thinking about the representations of the fundamental groups. There's really three different interpretations of Teichmüller space. One in terms of hyperbolic metrics, one in terms of conformal structures, and one in terms of representations of fundamental groups. And we all slew backwards and forwards between those. And it's really the group theory one that I'm most interested in. So then, if you have a good set of coordinates, what do mathematicians like to do? We like to generalize. So Coriniotis and Tan independently. Now, pause a moment. On Peter's picture from Anoia, there was Christos Coriniotis right in the front row there. So Coriniotis and Tan, they independently generalize this to the case of quasi-Fuchsian groups. So here I'm thinking about representations to SL2C, and I'm thinking of the connected component of discrete and faithful type preserving maps containing the Fuchsian representations. Goldman generalized them to convex RP2 structures. So this is where we're taking representations to SL3R, and again there's some geometrical things behind that, and the Fuchsian groups are sort of contained in there as a special sort of subset. And then together with Yannis Platis, who was a PhD student of Coriniotis, we generalize this to the case of PU21, which is the holomorphic isometry group of complex hyperbolic space. So now we have some beautiful original coordinates and then a zoo of generalizations. Well, and all the generalizations, they all sort of look a bit different, and it's a little bit confusing. So what do we want to do? We want to try to find a uniform setting where all of these are beautifully contained and we can understand how they relate to each other. So we're always told now by education theorists we should have aims and objectives. So I can never remember which one's which. So my aims and objectives are to generalize Fenchel-Nielsen coordinates to SL3C representations. And this is part of the PhD thesis of my student Rodrigo Davila, whose his PhD is in Mexico at Unam, and we want all of those previous cases, so the Fuchsian, the quasi-Fuchsian, the convex projective, and the complex hyperbolic. We want all of those to be beautiful subspaces, which we can really just read off from my coordinates in an easy way, and I can sort of work out how I can pass between them. So if you give me a convex projective structure and a quasi-Fuchsian structure, and a path between them that never goes through the Fuchsian locus, I can see how to pass between them. So the coordinates with direct generalizations. Now to do this, sadly this is a geometry conference, we're going to lose a lot of the geometric features because SL3C naturally acts on CP2 as a sort of generalization of the way the Riemann sphere point of view for climbing groups, but we sort of lose the bit that would be the hyperbolic geometry side of it. So we're going to reinterpret everything in terms of linear algebra, so it's going to be traces and eigenvalues are going to be the main things we're going to use, plus a little bit of combinatorial group theory as to how to build these surface groups. Okay. So let's do a little history lesson. This is what Fenchler and Nielsen did back in the 40s. And so their construction is all framed in terms of geometry. So this section is the one which has all the geometry in, and we're slowly going to lose geometry as we go. So we've seen this many, many times already. We're going to divide my surface into a pair of pants decomposition, which has got 2g minus 2 pairs of pants and divided by 3g minus 3 curves. And you will notice that I've chosen one, this is just purely for convenience for the rest of the talk, I've chosen one where every time I'm capping off a handle or closing up a handle, that happens within the same pair of pants. But that's just convenience for what happens later. We could just sort of fiddle around and do other things as well. And that choice is going to be fixed once and for all. Right? And that's the same, that's classically what Fenchler and Nielsen would do. Right, and of course, as Vivica was doing yesterday, I'm going to sort of pass between homotopy classes of simple closed curves and the geodesic in the homotopy class when I have a hyperbolic metric. And I'm going to do that without comment. So let's think about what happens with a pair of pants. So it's a three-hole sphere. I want to orient the boundary components. So we've had a lot of things where people say, oh, we don't care about orientation. I'm going to fix an orientation. And I do that in such a way that going around alpha, then beta, then gamma, assuming I'm reading from left to right. I never know whether I should read from left to right or right to left in these things, but in whichever way we do this, this is going to be the identity. So you can see this by kind of, you first go around alpha, to the middle of the back there, and then maybe I go around, however it works. And I've checked that diagram a lot of times, and I believe that's the right orientation. So the fundamental group is a free group on two generators, but the name of the game in everything we do is we want it to be completely symmetric along cyclic permutation of the three boundary components. So I'm going to write my fundamental group as generated by the free homotopy classes of alpha, beta, and gamma, with the relation that the free homotopy class of alpha, beta, gamma is trivial. Okay. And basic fact from in hyperbolic geometry, we've heard this lots of times. The hyperbolic metric is completely determined by the hyperbolic lengths of those three geodesics on the boundary. This is something we all know. Right. And so now let's think about how we glue them. If I want to glue y and y prime along alpha and alpha prime, then there's two things that need to happen. First of all, they need to have opposite orientation, otherwise we get something that's like a turn up in a pair of trousers, rather than sort of properly gluing together. And we need to have them to have the same length. And of course we have freedom as to how we glue, so we can twist them around here, and the way I'm choosing to do this, there's various conventions, I'm choosing to make so if that's my reference surface where there's no twist, then I'm just twisting along by a hyperbolic distance T alpha, and T alpha could be negative if I twist it in the opposite direction. So I'm not normalizing this with respect to the length of the curve. I could do that so that a whole twist, one twist, but there's different normalizations. I'm choosing to do it like that. Okay? Right, so then the next thing we can do is we can close a handle, and for convenience I'm just closing a handle within the same pair of pants. I'm doing exactly the same as on the previous slide, except that I'm just taking two boundary components of the same pair of pants and gluing them together. So once again, we need them to have opposite orientation, and we need them to have the same length. And again, I can do a little twist there. If that's my reference surface, then I twist that. The key fact is that the hyperbolic lengths are intrinsic. The twists always they're always relative invariance relative to some initial choice that I have chosen once and for all. You may choose it so that all of the orthogonals nicely meet, or you can choose it however you like, but the twist is always twist relative to some initial thing. So you can't just read off the twist so easily from the group. Good. So then that's all the ingredients of Fenchler-Nielsen. They use this like hyperbolic Lego, so we build up our surface from all these pairs of pants. We know how to do the structure on each pair of pants, and we know how to glue them together. So let's just do a little parameter count for fun. That we have 2g minus 2 pairs of pants, so that each one is determined by the length of three edges, so I get 6g minus 6. And now I want to glue along these curves, so that gives me 3g minus 3 conditions. And so that takes me down to 3g minus 3 parameter degrees of freedom. But then I have an extra twist parameter, which takes me back up to 6g minus 6. I suppose one of the things I forgot to say way back, so to emphasize it was on the screen, is the dimension of my space should be 2g minus 2 times the dimension of the group. And as SL2R has dimension 3, think of a matrix, has 4 entries, one condition that the determinant, so that's 4 minus 1 is 3. Okay, and so here we go. This is the theorem of Fenchler-Nielsen. Any hyperbolic metric is uniquely determined by all of these different lengths, which are positive real numbers, and the twists, which can be positive or negative. Moreover, if you give me a set of numbers that are 3g minus 3 positives and 3g minus 3 reals, then I can build you a surface. Now, that condition goes away for all of the generalizations. That's pointed out for the quasi-Fuchsian case. We know that the boundary looks like a fractal curve, and so there's no way I would get some algebraic conditions for that. Right, so that is the end of the first chapter. So let's do the whole thing again without using geometry, but now using matrices. First of all, I need to uniformize my pair of pants, so I'm going to write it as the quotient of the hyperbolic plane by a Fuchsian group. So that Fuchsian group is going to be the representation of the fundamental group of this pair of pants. Now, of course, as we've seen probably in the last talk, really I should be having infinite cuffs on the end here, corresponding to all of these other points. And so I'm sort of being slightly ambiguous there, so I'm not really writing this as the quotient of the hyperbolic plane. I'm actually writing it as the Nielsen region, or the convex hull of the limit set. But there we have that's the picture. And so now let's think about how to do all this with matrices. So our fundamental group of a pair of pants is a free group on 2 generators, and And way back in the late 19th century, Fricker and Vogt told us how we could parameterize all representations to SL2C, in fact, certainly to SL2R using traces. And so that representation is determined exactly by the trace of A, the trace of B, and the trace of C. So that's beautifully symmetric in my three boundary components. Okay, so that's just the this comment I just made about the dimension. Now, notice I've suddenly slipped away from PSL2R to SL2R. When I live from there, well, then I have a choice of sign for each trace, but the sign of the product is well defined, given that I'm assuming that ABC is the identity and not minus the identity. And there was a folk theorem that was a folk theorem for a long time, and then a proof was carefully written down by Gilman and Maskett, saying that if you have if this free group is the fundamental group of a pair of pants, then this product of the traces has to be negative. And so, for reasons of symmetry, I'm just going to take each of the traces to be negative, and I know how, using hyperbolic geometry, I can relate them, the trace and the length. And so this theorem of Fricker and Vogt is just the matrix version of the same metric is determined by the three lengths. Very well known, but just a beautiful connection there. So that's how we get our matrix version of the hyperbolic metric on the pair of pants. Now how do we glue? Okay, so then here we've got two pairs of pants, y and y prime, with the fundamental groups A, B, C and A prime, B prime, C prime, so that their product is equal to 1. So remember, what did I need? I needed alpha and alpha prime to have opposite orientation, and I needed them to have the same length. So opposite orientation, well, same length means that they're sort of in the same conjugacy class up to taking inverses, and opposite orientation means that A prime is conjugate to A inverse, and so I'm just for the moment going to assume that they're the same. So A prime is A inverse. That's the equivalent of the same length and the orientation condition. Okay, and now how do I glue these together? Using the language of combinatorial group theory, I do it using a free product with amalgamation. So I say that I just take the two groups, and the only relation I have is that A prime is A inverse, or the only new relation I should say, and so then that gives me a group, which I can write as now a group on 4 generators with the product being the identity, which you could think of as going around all 4 boundary components, but I can recover that by writing this relation. I can divide it into 2 parts. Now remember, A, B, C was the identity, so that becomes A inverse. A prime, B prime, C prime was the identity. That's A prime inverse. A inverse is A prime, and hey presto, I get that relation. Okay, so now what happens when we want to close the handle? I have the same sort of idea. Now I have to have B and A, B is conjugate to A inverse. That's the same as the opposite orientation and the same length. And so I can write B as a definite conjugate there. And now to close the handle, I take the H gen N extension, which means that I adjoin this conjugating element D, and the only new relation I introduce is that. And so when I do that, my relation ABC, I replace that with this, which becomes the commutator is equal to 6. And so this is really just saying that my fundamental group now is generated by 3 things. The commutator of 2 of the curves is the boundary, which is the well-known presentation for the punctual torus, or torus from the boundary. Okay, so now how do I twist? So those are the pictures that we had before. So let's now just think about this uniformized picture. So that was my uniformized picture without a twist. And what do I do? Well, I'm going to also assume that that is the imaginary axis, so here's the origin, and so my map A is just a diagonal map. So what do? I hold this one fixed, and then I dilate that. That's what translating along that geodesic by a hyperbolic distance of T alpha would be. I would dilate over that. So that dilation is just a hyperbolic isometry with the same axis as A. So it's something in the centralizer of A. And so I conjugate my right-hand group by that, and then I can still glue using the free product with amalgamation. So what I've done here is I've just translated everything in the Fenchel-Nielsen twist language into purely combinatorial group theory language. And so you can check that then what's happening is I then get this group B and C the same, I get the conjugates there, I get this relation, but remembering that K commutes with A, that just is the same as this relation here.
Sorry, John, I just can't read this. One thing I can't read, it's just this green text on the, there, that.
Dilate.
Oh, dilate, okay, thanks.
Okay, so that's what that top picture, that's just a repeat of that picture there. So we do the same thing here. Instead of taking my conjugating element to be D, I take it to dk, where K again commutes with A, and I get the same thing. So that's very, very similar. It's just, I'm just repeating it that, but just using that with the HNN picture. Great. And so now I can now reproduce the Fenchel-Nielsen results simply using matrix language. So what am I going to do? I'm going to take loxodonic maps AJ, BJ, CJ, and SL2R. I'm going to be so that the products of the three of each triple, AJ, BJ, CJ is the identity. So that's going to be determined by 6G minus 6 parameters, namely all of the different traces. I'm going to use the Pants decomposition as a recipe for how to glue things together. And to do that, I need those they need to be AJ and K, they need to be like that. I'm deliberately writing this as an inverse because later on we're going to need that. And to close a handle, I'm going to need this thing. These are 3G minus 3 conditions, so I get 3G minus 3 parameters, just like we had before. And when gluing at AJ, I twist using KJ. KJ is in the centralizer of AJ, and so I get different parameters there. Total of 6G minus 6 parameters. And so that's given me my Fenchel-Nielsen coordinates. Just a note then, that after gluing but not closing handles, I'm going to get something where I have 2G generators whose product is the identity. Closing the handles in each case turns each pair into a commutator, and then I get the usual presentation of a surface group. So that's just a nice way of constructing how you get the usual presentation for a surface group. Sort of from the nuts and bolts sort of way. Okay, how are we doing? Good. So now we're going to think about the SL3C case, and this is going to be, I want to use the previous chapter as a recipe. And so the first thing we're going to need to do is we're going to need an analogue of the Fricker-Vogt theorem. How do I parameterize, using traces, the fundamental group of a pair of paths? Right? But first of all, because I've forgotten which slides were coming in, we need to have a little introduction slide. Right? So here's a knowledge bomb for you. We want to have 18G minus, no, we want 16G minus 16 complex parameters, right? Because we need 2G minus 2 times the dimension of the group. The group's 3 by 3 matrices, so that's 9 entries, 1 relation, and the determinant is 1, so the group is 8-dimensional. So we need 16G minus 16 parameters. And if we were just having things to do with the curves like we had before, we would need that to be a multiple of 3. And for many genera, no, 3 doesn't divide 16. Right? This is your knowledge bomb. So we're going to need to do something a little bit more. We need to have some extra parameters that come from somewhere. So where do they come from? I mean, this was all in gold as well. This is not really a new knowledge bomb. Okay, so let's go. So here is a theorem which the version I'm using is in a paper of Lawton. The earlier version was written down but with no proof by when, at least no proof that I know of. He may have done something in Chinese, I'm not sure. And there was some earlier work by Teranishi. Preville also did things later, but really this is as written in Lawton. Every time I've given this talk or a similar talk, people say, oh, but it was done earlier by so-and-so, so this is my catch-all thing. So I've got, where are we? We've got this ABC. ABC is the identity sitting inside SL3C. How do I parameterize that? Well, it's parameterized up to conjugation by the traces of 9 group elements. So A, B, and C, they're inverses. Remember now that there is no relation between the trace and the trace of the inverse. We have the commutator, which is nice, and then we have this A inverse B and B inverse A. Right, what's the problem here? We have 9 traces, we have dimension 8, so there should be some relation. What is the relation? Well, the relation is that the trace of the commutator and the trace of the commutator the other way around are roots of a quadratic polynomial whose coefficients are polynomials in the other 8 traces. Right? And if you want to write them down, you can do. It takes an entire page, practically, of LaTeX to do that, but they are indeed polynomials in the other traces. So if you try to manipulate them, it's a little bit of a mess. But nevertheless, they are these. So really, to this trace here, all I'm asking for is a choice of root. So I could think of that as a plus or minus sign in the middle of the quadratic formula. Right? So I'm going to be referring to this later as a choice of sign. And in some sense, this is to do with the orientation of the surface and how it relates to the complex structure. Okay, so here these traces are beautifully symmetric in A, B, and C. We know that the trace of the commutator of A and B is the trace of the commutator of B and C, is the trace of the commutator of C and A. So that's symmetric. Ditto for the commutator the other way around. The problem is we have these two which look very, very unsymmetric in terms of A, B, and C. Here's a beautiful little result which shows that if that trace, that isn't symmetric, but if I subtract off trace of A inverse trace of B, then I get the same thing with them cycled around and cycled around. If I do it the other way around, I get those things. Right? So these are 2 bunches of 3 things. Now, the question is, do we want the proof of this or do we want to have an early coffee? I think we've got the time for the proof of that. So here's the proof. It takes 2 lines. So by the Cayley-Hamilton theorem, A satisfies its characteristic polynomials. Okay? Everybody happy? Basically linear algebra. So now I'm going to multiply this equation. So this O is the 0 matrix, this I is the identity matrix. Multiply on the right by A inverse B, but because ABC is the identity, that's the same as A to the minus 2C inverse. So I get this equation. Now I'm going to take traces and use the fact that a constant multiple of a matrix, the trace of that is that same constant multiple times the trace. Take traces and rearrange, and hey presto, I get the first line. All of the rest of them are the same. Isn't that beautiful? So, what parameters have I got for a pair of pants? Well, I have 3 boundary curves, so I have six complex boundary parameters. Trace of A, trace of B, trace of C, trace of A inverse, trace of B inverse, trace of C inverse. And because we're in SL3C, there's no relation between those traces. Those are independent parameters. Whoops. I have two complex shape invariants, which remember that those are symmetric under cyclic permutation, but again they're independent of each other. And I have a choice of a root of quadratic polynomial whose root is the commutator. So that's my choice of sign. So I get 8 complex parameters plus 1 zero-dimensional parameter. That's a plus or minus. So now I can use group theory to close the handles. It's exactly the same thing. We have a free product with amalgamation for gluing 2 pairs of pants, and we get an HNN extension when we're closing a handle. So here we go. Whoops. Yeah. So, no, here we are. So in order to glue A and A prime, we need trace it with A to be conjugate to A inverse, so trace of A prime. So those are two independent conditions that we need now, rather than just one. But then we get free product with amalgamation before. To close the handle, we need, again, 2 independent conditions, and we get the HNN extension as before. And then we use the pants decomposition to glue all of these, and we get the fundamental group on the surface, just as we did before. Now we need to describe twisting. Right, so what do we need to do? Just as before, we need to change that by a K. That was a K that's in the centralizer of A, so that was this thing where we hold one side fixed and we dilate the other. And similarly, when we're closing a handle, we have another K which commutes with A, and we put in a DK there. This is exactly the same as we had before. So now, how to see what the parameters associated with this, what the analogue of the twist is. We have, so assume that we've got A, strongly loxodromic, all of its eigenvalues have got distinct modulus, their product is equal to 1. And so I'm just going to assume that they're just done in size order. So I want something in the centralizer of A, so that's also going to be diagonal, because well, it just has to be. And so what I'm going to do is I'm going to write this K as T times S, where these are diagonal matrices, so canonical diagonal matrices. The first one has a 1 in the middle, and then the inverse elements first and last. And the second one has the same first and last, and the middle one is the reciprocal of their product. And I'm going to write these as e to the something all the way through. And so t is going to be called the twist, theta is going to be the, sorry, t is the twist, theta is the bend, and then over here, S is the bulge, this is a Goldman term, and phi is, this is a new one, we're going to call this a turn. So and we have twist, bend, and bulge, turn, they're complex parameters. And so, let's put all of this together, because it's almost coffee time. So I've got strongly loxodromic, so that means that I've got distinct modulus of eigenvalues, all of them, because this is just a patch of the representation space, but that's going to contain all of the things that are going to be my interesting deformation spaces, so I'm only interested in that patch of the space. That's again just like we saw in Kuriotis and Tan. I should say, for those people who are used to things like higher Teichmüller theory and SLNR representations, for the convex projective representations, and these form a component of the representation variety. For the other cases, it's not a component, we can actually pinch at a finite. So there's different cases around here. But anyway, for the SL3C, we definitely don't get a second component. Right, so we have these matrices, just like before, which are going to correspond to my pants curves. We have these fundamental groups for each pair of pants, just like before. So these are determined by all of the boundary parameters, the AJ, BJ, CJ, A inverse, B inverse, C inverse. It's shape invariant for each, so there's how many of those? Well, there's 3g minus 3 times that, and then here we've got 2g minus 2 times these pair, and so that gives me 16g minus 16 complex parameters, which is the right number, and 2g minus 2 choices of sign. These are the things to do with these roots. Now I use the Pants decomposition as a recipe of how to glue. I'm going to get complex. So I'm going to get for each curve. I'm going to get 2 complex conditions. So those are 6g minus 6 complex conditions. I'm left with 10g minus 10 parameters. But when gluing, I can get a complex twist bend and a bulge turn parameters. So I'm going to get 6g minus 6 more complex parameters. Again, relative, just like we had before. They're not absolute invariants, they're relative to some fixed starting surface. And that's 16g minus 16 complex parameters plus 2g minus 2 choices of sign. And those are my Fenchel-Nielsen coordinates. Right, how does this relate to all of those special cases that we saw before? So now let's think about the special case of the Fuchsian groups. Now I'm needing to think of the irreducible representation of SL2R into SL3C, and so that is actually SO21. Here we have the traces, trace of an element is equal to the trace of its inverse and is equal to real, that's real. So that gives me some sort of linear slice through the middle, because I'm setting various imaginary parts equal to 0, and the trace and the trace of the inverse, so it's like a diagonal slice. It's just a nice linear subspace at the moment. I get a twist parameter, but I don't get a bend, I don't get a bowl, and this is really just the original Fenchel-Nielsen twist that we had before. It's the same as this T that I had on this slide there. That is the Fenchel-Nielsen twist. I have no bend parameter, no bulge, no turn, so all of those were sort of in a 0 slice of that. Well, I say no shape invariance. The shape invariance, this is like a function of the other traces, and so we somehow get something that's like a graph of a function. So it's not quite a linear subspace because there's a rather slightly more complicated function there. I don't need a choice of the root for A and B because this is a perfect square. It's a repeated root in that quadratic polynomial. And that gives me my 16g minus 16 real dimensional subspace sitting through my, my 6g minus 6 inside my 16g minus 16 dimensional subspace. If we have SL2C, so the irreducible representation is the complex orthogonal group, SO21C. It's not the unitary group, it's the complex orthogonal. So that, here again, the trace is equal to the trace of the inverse. That's now a complex number. We have a twist and a bend. These are the usual twist bend from the quasi-Fuchsian world. We have no shape invariant, or rather we have a graph. No choice of a root. Again, we have a repeated root of that quadratic polynomial. I get 12g minus 12 real, or in fact 6g minus 6 complex dimensional subspace. Now for SL3R, the traces are both real, but they're independent from each other, so that's a different equation in my parameter space. I have twist bulge parameters. These are both real parameters, but I have no bend and no turn. I do need shape invariance. Goldman has slightly different parameters here. They were symmetrized by Zhang, but they are slightly different from the parameters I have, and I can write a way of getting from one to the other. And I do need a choice of a root for this commutator equation. So I now get a 16g minus 16 real dimensional subspace. And finally, representations to SU21, so this is the complex hyperbolic case. Now the trace of the inverse is the complex conjugate of the trace, so that's another diagonal slice. I have a twist and a turn parameter, but no bend and no bulge. So when Yanis and I were writing our paper, we used twist and bend which was actually a bad mistake. We should actually have said twist and turn. We need the shape invariance, we need the choice of the root, and so what happens is somehow in the middle we have the Fuchsian groups, and we have all of these in this sort of 6G minus 6 real space, and we have all these other parameter spaces that are effectively linear subspaces or linear graphs over linear subspaces, all sitting in my big space. And so now I could potentially pass from one to the other without going through the Fuchsian locus. There's lots of interesting things yet to be discovered there. As I said before, in this case, that forms a whole component. So if I go to the boundary of the space of this slice, well, the boundary of the discrete and faithful subspace, I go to the boundary of the whole space. Same here. This is the Hitchin component. I go. Whereas here, if we know classically that we can do all sorts of exciting things on the boundary. We can pinch curves. We can also go to geometrically infinite representations. In this case, we can pinch, but conjecturally, that's all we can do. And so this one should have like a fractal boundary. This one should have in some sense, a polyhedral boundary where we divide it up into algebraic subvarieties, real algebraic subvarieties. So that's two different sorts of boundary behavior, whereas these have no boundary, and so no boundary behavior. And so then there's lots of interesting questions about how you would go to the boundary for more general representations and how you would interpolate between them. But that's all. Thank you for listening.
Do you know if you stay near the Fuchsian locus, if all those representations are discrete and faithful? Is there some sort of stability?
Yes. That's basically using the sort of hyperbolic groups, and there's like an open condition. So I think that's Guichard, I think. So if you're working in hyperbolic, it's an open condition, so there's an open set, there's an open neighbourhood there. I mean, there's various proofs I know, but that's the one that I think. So Guichard has a statement to that effect. So all I'm really thinking about is I'm just interested in the connected component containing the Fuchsian locus, but that is open maximum convention.